This is a video on the electromagnetic spectrum, specifically how white light can be separated into different wavelengths, what electromagnetic waves are, and how wavelength relates to scale and applications found in everyday technology. My name's Mr. Head, and welcome to MN Horizons. For most of human history, light could only be understood through what we could see with our own eyes, but as we'll soon discuss, visible light is just one small part of a much larger story. If you pass a beam of white light through a prism, something interesting happens. Instead of staying white, the light spreads out into a range of colors: red, orange, yellow, green, blue, and violet. This happens because white light is not a single type of light. It's a mixture of many different wavelengths traveling together. When light enters a prism, each wavelength bends by a slightly different amount. Shorter wavelengths bend more, while longer wavelengths bend less, causing the light to separate. What comes out of the prism is only a small slice of a much larger system known as the electromagnetic spectrum. The colors we see are called visible light, and they represent only the wavelengths the human eyes can detect. On both sides of the visible spectrum are forms of electromagnetic radiation that are invisible to our eyes. These waves follow the same basic rules as visible light. They just have wavelengths that are either longer or shorter than what we can see. To understand the electromagnetic spectrum, we first need to understand what a wave is. A wave is a way energy moves through space as a repeating pattern rather than matter traveling from one place to another. For electromagnetic waves, this involves electric and magnetic effects moving together through space. But that level of detail goes beyond the scope of this video. Instead, our focus is on a variable of waves called the wavelength. Wavelength is the distance between repeating parts of a wave, such as peak to peak. Changing the wavelength changes how the wave interacts with matter, which is why different parts of the electromagnetic spectrum behave differently and are useful for different purposes. When we organize electromagnetic waves by wavelength, we get the electromagnetic spectrum. The categories we use are created by scientists to help describe how these waves behave and how we use them. Each part of the electromagnetic spectrum includes a range of wavelengths. To make the scale easier to visualize, we'll use a single reference size for each band, not as an exact value, but as a helpful comparison. At one end of the spectrum are radio waves. A helpful reference wavelength for radio waves is the length of a football field. Because these waves are so large compared to most human-made objects, there are only a few things that can disrupt their motion, allowing them to travel long distances. Radio waves are used for radio and television broadcasts. Next are microwaves. A useful reference size for microwaves is about the size of a tennis ball. These wavelengths are commonly used for wireless communication like Wi-Fi and cell phones. Microwaves are also used in microwave ovens to heat food. Moving to shorter wavelengths, we reach infrared radiation. A helpful reference size for infrared is about the size of a grain of sand. Infrared radiation is closely connected to heat. Warm objects emit infrared radiation, which is why infrared cameras can detect heat. The next region is visible light. A reference size for visible light is about the size of a red blood cell. This is the only part of the electromagnetic spectrum that human eyes can detect directly. Visible light allows us to see colors, shapes, and motion. Beyond visible light is ultraviolet radiation. A useful reference for ultraviolet light is about the size of a virus. Ultraviolet light from the sun can cause sunburn, which is why sunscreen is important. Ultraviolet light is also used for disinfection. At even shorter wavelengths are X-rays. A reference size for X-rays is comparable to an atom. Because of this scale, X-rays can pass through soft materials but are absorbed by denser ones, making them useful for medical imaging. Finally, at the shortest wavelengths are gamma rays. A reference size for gamma rays is comparable to an atomic nucleus. Gamma rays carry very large amounts of energy and are used carefully in medical treatments like radiation therapy. This will all be important to know because early studies of space relied only on visible light from stars, but over time astronomers expanded their observations to include invisible parts of the electromagnetic spectrum, opening new ways to learn about the universe. To summarize, visible light is only a small part of the electromagnetic spectrum. Different wavelengths of electromagnetic waves behave differently, allowing us to study and use light far beyond what our eyes can see. This idea is a critical foundation for understanding Minnesota Standard 9E3211. Construct an explanation that links astronomical evidence of light spectra, motion of distant galaxies, and composition of matter in the universe to the Big Bang. Thanks for joining me on MN Horizons.